very much.
Thank you all for coming out. It's been Phoenix, none of you have been here with a snowstorm. But this isn't a snowstorm for you, I know. So, but thanks anyway. It's a pleasure to see all of you tonight. And I hope we'll have some fun. I'll stare at that thing staring at me, but it's okay. I put on some stuff that's primarily so you could have something to read while I was being introduced, which I find is useful. But this actually is one of my favorite quotes because it epitomizes to me this. I'm going to try and move this down. It's a little loud. In fact, I'll put this volume down a little bit. Maybe.
We can't hear you.
You can't hear me? Now you can?
Yeah, it's better.
Okay. See if it. Okay. Good. Well, you let me know. If you can't hear me, you're not missing anything, so it doesn't matter. I guess I can't. Okay. We'll see how. Well, maybe these things are turned on. Anyway, I like to get close, so I don't want to be stuck back there. In any case, this is one of my favorite quotes because it epitomizes what science is all about and what I want to talk to you about, which is really ultimately a mystery story. But the biggest question is, of course, how we got there in the first place, which is, in this case, the question of why is the universe here? And why is there something rather than nothing? That's a question that's been around for as long as people have thought about questions. It's traditionally been a religious or a theological question, but it isn't a religious or a theological question, because, as I'll point out, something and nothing are physical quantities, and therefore it's a scientific question. And science has completely changed the playing field of that question. Now, maybe this is true in Calgary. I used to live in Cleveland, and I used to have to tell people that these are stars. But, I don't. But the universe is remarkable. Look out at the night sky, and it's clear, and you're away from the city. And it is remarkable. It's a globular cluster, but it doesn't really matter whether you're looking at that or anything else. And as beautiful as it is, what we've learned in the last century or so is that all the stuff we can see is just the tip of a cosmic iceberg of stuff we can't see that has changed our picture completely of not only the present universe, but the past and the future, as I'll describe. And changed our picture, in fact, of as we get closer and closer to understand perhaps how the universe began. And what I want to talk about tonight is an amazing result, a series of results, that in fact we now plausibly can understand how a universe could come from nothing. And it seems to me that is an idea that is ultimately worth celebrating, as I'll describe. So this question has many different ways of answering it, as I pointed out. There's a lazy answer, which is this one. That doesn't tell you anything. It doesn't explain anything. It's just ultimately an intellectual cop-out. And what is really important is if we really want to understand how the universe began, we should look at the universe and not just think of it or get a revelation. So we really want to look at that universe of stars. And that has caused us, over the last century, perhaps in one of the most exciting intellectual roads and struggles, step by step, to come up with a picture of the universe which is stranger than we could have ever imagined. That's the other thing I want to emphasize tonight, is that the universe is indeed stranger than we can imagine. And the actual universe is far more interesting than the universe of myth or fairy tales. And I can't understand why people seem to think it's somehow less inspiring than words written thousands of years ago by people who didn't even know the earth went around the sun. In any case, so let me begin slightly differently on this mystery story. It was a dark and stormy night. Now, by that, I'm not referring to the beginning of the universe, but rather to the night that Albert Einstein dotted the last period on his most famous set of equations, most important set of equations, his discovery of the theory of general relativity, which was a theory not just, was a theory of gravity, but it was actually much more than that. It was a theory of space and time. It was the first theory of space, in fact, but it was not a theory of just how objects move through space, but how space itself. Damn this thing. Well, I'm gonna, you know what, you gotta see if you can turn that off. That might be causing that. Is your, you introduce me. Where's your microphone off? Or were you on? Okay. Well, we'll see. Okay, anyway. So it was not just a theory of how things move through space, but how space itself moves. Space in fact, according to general relativity, is dynamical. It responds to the presence of matter. And it's a beautiful theory, and in fact, since it was a theory of space, it was the first theory of the universe. And Einstein knew it was, and he knew it was right. There was a small problem, however, and that was that it didn't describe the universe in which we lived. Nowadays, that doesn't seem to bother physicists too much, but it used to. And Einstein was quite worried about that, and he revised his equations in a way to accommodate that. He was a very creative guy, and he realized he could revise them in a way that was consistent with all the symmetries that had led him to develop these equations, and it could describe the universe in which we lived. In 1916, the universe in which we lived, in which Einstein lived, was static and eternal. Conventional scientific wisdom was that the universe had been around forever and would be around forever in more or less the same way. If you look at the stars night after night, they're the same. So it seems reasonable to assume that. But there's a problem. And there was a problem with general relativity, and there was a problem with Newtonian gravity. Anyone who's taken physics knows that gravity sucks. It always pulls. It never pushes. And if you put a bunch of stars out there, you wait long enough, their gravitational attraction will all cause them to collapse together. And you couldn't have a static universe. Things wouldn't stay there. So as I say, he revised his equation just a little bit, and I want to show you how. And we'll try and lock the doors now. Okay. I want to show you Einstein's equations. Now, I've written them in a user-friendly form here for the biologists. There we go. Turn it down a little bit. I was thinking I was going to do that myself. Okay, let's see if we get feedback. Let me walk here and see if we get feedback. Well, not as bad. No, hear it? I hear it. Does this mean I'm gonna? Yeah, that mic is not on, I think.
No problem. I think it's from the speaker.
Could be from the speakers. Okay, I'll stand behind the speakers. The speaker will stand behind the speakers. Are we okay? Did you get okay? I got this one on. That was from my computers. Okay. Let's see. That may be a little bit better. It's a little bit less loud. Can you still hear me? Yeah. That's much preferable. Okay, good. I think we got it. Okay. So, now you've had time to stare at this equation and work it out. And it's a little easy. The left-hand side is equal to the right-hand side, but it's not completely facetious. Because in general relativity, the left-hand side relates to the geometry of space. Space itself can curve in the presence of matter. So all the geometric quantities are on the left-hand side, and the stuff that causes the curvature of space, the energy and momentum of stuff within the universe, is on the right-hand side. So this is the physical content of Einstein's equations. I'm a theoretical physicist, as was pointed out, and therefore I have to write down the Greek letters. There, that's much more illuminating. Now, this was the equation that had the problem, because this is the equation in which gravity sucks. And so Einstein realized that he could add an extra term to the left-hand side of the equations. And it's a term he called the cosmological term. And this term would produce a small repulsive force throughout all of empty space. So small, it wouldn't affect any of the results of the planets orbiting the sun, the beautiful results that led Newton to his theory of gravity. But on the other hand, it could build up over the scale of the universe and perhaps hold distant stars apart. So he thought this would result in a static universe. And the problem was, of course, lots of problems happened. And in fact, almost immediately after he wrote it down, he called it his biggest blunder. This is one of the reasons. This was a postcard I got when I was on sabbatical a bunch of years ago in Switzerland, from Einstein to Hermann Weyl, 1923. And Einstein said to Weyl, Weyl was a famous mathematical physicist, if you get rid of a quasi-static universe, then out with the cosmological term. Because he realized already in 1923 it was beginning to be understood that the universe wasn't static. And if you have this universe that isn't static, you don't need this universal repulsive force. Because if the universe is expanding, in fact, gravity can be purely attractive. It can slow the expansion of the universe and maybe stop it and cause it to recollapse in the reverse of a Big Bang, or not. And that became the central question of 20th century cosmology, is how will the universe end, with a bang or a whip, basically. And he realized he didn't need this term anymore, and he wanted to throw it out. He called it his biggest blunder. Now, already, as I say, by 23, he was people were beginning to think the universe might not be static, but the person who lives the world of this is this man here. He's one of my heroes.